Okay, let's continue. As we said before, we want to start with the exercise. I hope that you was able to resolve it. So it's a simple application regarding SDCCH channel. So here we have a GSM operator. We have a GSM operator with a 63 frequency and with a reuse factor of 9. So we have 63 frequencies. 63 frequencies and reuse factor 9. Reuse factor cluster size equal 9. This means that we have 63 over 9 equals 7 frequency per cell. So in each cell, we have one time slot, which is 1 IT reserved for the BCCH channel, and 2 IT are allocated or reserved for SDCCH channel. So in each cell, the traffic is characterized as follows. So we have 25 millierlang per subscriber at peak hour, and the peak hour, the call rate is 1 call per hour, and the blocking probability is 2 to power 10 minus 2, which is 2%. And the location update rate is 1 location update every 60 minutes, which is mean that we have 1 location update every 1 hour, sorry. And for the occupation of the SDCCH channel, we have at each time we are using it, we have authentication and ciphering. It's 5 seconds. And when you are doing the location update, it takes 0.6 second. And if you send message, the rate of the message, the transmitted message is 0.6 message per hour, and the received message is 0.6 received message per hour. And the occupied time of the SDCCH is 5 seconds for a message. So here are the data related to this configuration. And now the question is, we want to show that the allocated SDCCH channel for a blocking rate of 1%. So for the SDCCH channel, the quality of service is 1%, which is 10 to power minus 2, is respected by the reservation of 2 IT. So here we want to show that if in each cell we allocate 2 time slot for the SDCCH channel, which means 2 physical channel for the SDCCH channel, it's enough. So it's respected. So that's why let's start by knowing how to deal this. So in order to see if the allocated SDCCH channel are enough for the cell. So in this case, we want to know the traffic in the cell. So we want to know the number of the user in the cell and the traffic, the signaling traffic generated by those users in order to see if the allocated time slot for the SDCCH channel are enough. So that's why we want to find the number of users. So here, let's start by having the traffic. So in this case, if we have 7 frequencies per cell, so 7 frequencies per cell, this means that we have 7 times that, which is equal 56 time slot. Okay, and we remove 3, which are 1 for the BCCH and 2 for the SDCCH. So we have 53 IT that could be used for the traffic, okay, channel for the TCH. So in this case, if we have 53, donc in this case, we can see that using those 53 TCH channel with blocking probability of 2 times 10 to power minus 2, here the traffic that could be supported, here it's the traffic, that TCH traffic, it's based on the table, we can have up to 43.06 Erlang per cell. So in this case, this is the maximum traffic, let's say the voice traffic or the TCH traffic that's supported by a cell. So in this case, if each user generate around 25 millierlang, so we are able to find the maximum number of users that can be supported. So the number of subscriber in a cell, this is the maximum number, is equal to 43.06 Erlang over 25 millierlang. In this case, it's around 1,722 subscribers. So we want to see now, because this is the maximum number of users that could be supported in the cell, taking into account the available channel for the traffic. So let's see how what's that signaling traffic generated by those users. Okay, so in this case, we want to find based on the signaling. So we have signaling location update, we have the establishment of the call, and we have also for the SMS. Those the traffic, if you remember here, those here we can calculate the occupation of the SDCCH channel for the call, for the location update, and for the SSM. And after that, we multiply them by the number of users in order to see the occupation of the SDCCH channel, which means that is the traffic, the signaling traffic that we should send over SDCCH channel. So in this case, let's calculate the traffic per user. So S, or let's say is the SDCCH signaling or traffic per subscriber. In this case, it's equal. We have one call. Let's see, we have one call per hour. Okay, and each call, it's around how many time? Here, for each call, we should make authentication, which is 5 seconds. So here it's one call per hour times 5 seconds over, because we are working on 1 hour, so let's use in second. So 3,600 seconds. This is for the call. Plus, if you want to calculate the location update, so the rate of the location update is 0.6. Okay, it's 0.6, and in one and the occupation is 0.6 second, and we are doing one location update every hour, so it's also 1 times 0.6 over 3,600 plus what we have for the SMS. So we have 0.6 as a rate for the transmitted and 0.6 for the receiving, so it will be 1.2 times for each one, it's 5 seconds over. Okay, so in this case, if we calculate those, we have the SDCS traffic per users, and in this case, it's around 3.2 millierlang. Okay, so here we have the signaling traffic or the SDCCH traffic generated by one user in the cell. If we want to have the total traffic, so in this case, I want just to add one slide. So the total SDCCH traffic in the cell, in this case, it's equal to the traffic per users times the number of users or subscribers. So in this case, it's equal to 3.2 millierlang times the number of its 1,722 subscriber, and in this case it's equal to 5.5 erlang. So we have 5.5 erlang. Okay, so in 5.5 erlang, and remember that the quality of service is 1% for the signaling. So in this case, with 5.5 erlang and at 10 to power minus 2, the required number of SDCCH channel based on Erlang table. If we want to check the Erlang table, I want just to check it. So for 5.5 and 10 to power minus 2, it will be equal to 12 SDCCH channel. Remember that those 12 SDCCH channel are logical channel, and from the course we know that we are able to multiplex 8 SDCCH channel over one physical channel, that is one time slot. So we are able to multiplex 8 SDCH logical channel over one time slot. So in this case, the number of reserved base station, sorry, the number of reserved time slots. So we have 2. So in this case, 2 IT are allocated. This means that we are able to multiplex 2 times that, we are able to multiplex 16 SDCCH channel could be supported in a cell. We need 12. This means that the allocation or reservation of 2 ITs is enough and is satisfied. Okay, could satisfy the requirement. So here, this is the answer of part A. In this case, this means that what we show that the reservation, it's okay. Now, for the second question, what's the number of supplementary SMS that could be supported over the SDCCH channel without change the IT allocation? Because we need 12 SDCCH channel and we are able to support up to 16 SDCCH channel. This means that we have 5.5 Erlang, but it's possible to have more than 5.5 Erlang as signaling. So if you want to change, or if you want to send SMS message, supplementary SMS message, it's possible. So how many SMS message you can change? Okay, this is the question. If you want to send more SMS, what are the number of SMS that you can send? So in order to do that, okay, in this case, we should know the total traffic, the total signaling traffic that you can support. So in this case, okay, we have, as we said, 16 SDCCH channels that are reserved. So with 16 channel, SDCCH channel, at 10 to power minus 2, it's possible based on the Erlang table, we can support up to 8.8.875 Erlang. So that's why it's possible for you now to add SMS traffic up to 8.875 minus 5.5, which is around, in this case, it's around 3.375 Erlang. So those traffic, you can add them as SMS. You just need to know how many SMS you can send. In order to do that, you just divide this by the occupation or by the Erlang generated by one SMS. Remember that one SMS, it's around 5 seconds over 1 hour. So if we want to know, okay, I want to add one more slide. So as I said, we have occupation of one SMS is 5 over 356. Okay, so number of supplementary SMS will be equal to the traffic that we can support, which is 3.375 over the occupation of one SMS, which is 5 over 3000. In this case, we can have up to around 2430 SMS. And in this case, you can, if you want, divide them to the number of the users, or you can, according to what you want. But this is the number of supplementary SMS that you can support in one cell. Okay, and we are working in peak hour. Okay, I hope that it was clear for you. And remember that the SMS messages are all sent over the signaling channel. Okay, this is one of the well-known characteristic of a GSM system. I hope it was clear for you how to make the dimension. For example, in this exercise, if the let's say if the allocated SDCH channel was 1 IT, in this case, 1 IT are not enough, okay? Are not enough. So if you want to make the exercise with 1 IT, you will find that you need traffic more than 8 SDCCH channel. You have traffic signaling traffic that require more than 1 IT that SDCH time slot. This is mean that it's more than 8 SDCH logical channel, and in this case the configuration is not respected. So you have to allocate 2 IT or 2 time slot. Okay. I hope it's clear. So let's continue. We already presented the dimensioning, and now we will start the link budget, and it's also one of the important part regarding dimensioning and the planning. And the link budget is very important in order to study the coverage of the cell, okay? Because we know it should be clear that any user, even if it's at the border of the cell, the user will be able to receive the signal and from the base station and to send the signal to the base station. So that's why in this case the link should be balanced link or liaison équilibrée. In this case, it should be asymmetric, okay, in terms of coverage. And typically we have what we call sensitivity at the receiver. In this case, we should be sure that the received power could be detected by the receiver in both sides, from the users and from the terminal at the user side, and from the base station at the base station side. So in this case, we have different parameters to be considered, like emitted power, sensitivity, coupler, duplexer, and so on. So let's see what are the different parameter. So here, let's say that we have a power transmitted by the base station. Okay, we have some coupler to connect the transmitter to the antenna. So in this case, we have a kind of loss due to the coupler. It's a loss here. And we have another loss due to the feed cable. And after that, we have the antenna. Typically, at the antenna, it's possible to make an amplification. That's why we have it as a gain. And over the wireless, it's a propagation. And in this case, we have the path loss. It's also a loss in the in the power. At the receiver, this is the user side, the terminal equipment side. Here we have the antenna. For the antenna here, we have also a gain of the antenna. And after that, at the local, we have loss due to the feed. Okay, and also we have here the received power. Okay, and here this is in the downlink. Okay, this is in the downlink. In the uplink, it will be the reverse position. The emitted power from the mobile. We have some loss here locally, and after that we have the gain of the antenna. We have the path loss over the radio interface. At the receiver of the base station, at the receiver, we have the gain of the antenna, and we have the loss of the feeder of the base station, and then we have the receiver. So that's why typically the way is working, and here we can find the received signal at the base station coming from the receiver at the users coming from the base station, which is in downlink. This is the downlink, and in this case, the received power is equal the transmitted power minus the loss. Okay, on the base station, the loss on the feeder, and the gain. We add the gain of the antenna. This is the pass loss, and we add the gain of the terminal, and after that, the loss of the at the terminal level. So this is typically the signal received at the mobile station. If you want to work on uplink here, and we want to find the received signal at the base station, here is the received power. Okay, it's equal the transmitted power by the mobile station, the loss at the mobile station, the gain of the antenna at the mobile station. So that's why minus loss plus gain minus path loss, which is in the uplink path loss. And we have the gain of the base station, the gain of the diversity, if you want here at the base station, it is the gain of the antenna and the loss of the feeder at the base station. So if you want to make the balanced link, so this is liaison équilibrée between uplink and downlink, so this means that we should find the path loss in downlink and the path loss in uplink, and the path loss in downlink should be equal to the path in uplink, because in this case we are sure that if the path loss is approximately equal, the mobile station is able to receive the signal from the base station, and the base station is able to receive the signal from the mobile station, from the terminal. Okay, and this is typically how to calculate this. So that's why it should be equilibrated like this, and we can tune the transmitted power, the gain of the antenna, a lot of parameters that we can configure. Typically, it would be the transmitted power, okay, in order to have uh, 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 path loss in uplink equal to the path loss in down. There is another well-known formula, which is the puissance isotrope rayonnée equivalent, which is the equivalent power of the antenna that is equal to the uh, uh, transmitted power, where we remove the loss of the cable and we remove the loss of the feeder, and we add the gain, which is the power before here, which is the power here before the path loss. Okay, this is typically we call it PIRE. Okay. So generally, if you want to take this example, Here we want to calculate the path loss on the uplink and the path loss on the downlink, and I guess you are aware about how to work with the dBm. dBm is the power. Okay, it's typically 10 log power over 1 milliwatt, and dB typically is the ratio of power. Okay, it's a ratio of power. So typically, let's consider the case of this is the downlink. Okay, this is the downlink. We have the transmitted power is 39 dBm. The path loss is 3.5 dB. Here, sorry, the loss in the cable, the loss in the feeder is 3 dB. The gain of the antenna is 14 dB. At the receiver, the sensitivity is 1 minus 102 dBm. So if you want to put it, so typically the received power at the mobile station, which is equal to 182 dBm, it's equal to the transmitted power, which is 39 dBm, plus here is the loss, so it's minus 3.5 dB. It's a loss minus 3 dB. Here it's a gain antenna plus 14 dB. So this means, so it's also, we have to remove the path loss in the downlink. So that's why the path loss in the downlink will be equal in this case to, if you want to calculate it, here we have 39 will be here minus 3.5 minus 3.5 plus 14, it will be around 7.5. Yes, 7.5 plus 39, it will be 46. Okay, and we come it, so it will be equal to 148.5 dB. Okay, that's the value. So this is the maximum path loss that's possible on the downlink is 148. Okay, I want just to be sure about the calculation. So it will be 3.5 plus 3.5. It's okay. Oh, it's 3. Okay. Okay. It's okay. So this is the downlink. So let's calculate it in the uplink. So in the uplink, we have the transmitted power is 30 dBm. Okay. And the received is, the sensitivity is minus 104 dBm, and we have gain and we have the loss. So typically in this case, in the uplink, so I will calculate here in the uplink. So this is the path loss in the downlink. Let's calculate the path loss in the uplink. In the uplink, in this case, there is the sensitivity at the base station, which is PR base station, PR BTS, which is equal 1 minus 4 dBm, is equal the transmitted 30 dBm minus the path loss. This is the path loss uplink. And after that, we have the antenna gain, it's 14, plus the gain of the diversity, which is 3.5 minus 3. And in this case, LP uplink will be equal, let's say 30. We have here 14.5, 14.5 plus 30, it will be 44.5, and from the other side 1. So it will be also equal to 1, okay, dB. So in this case, we found that the maximum path loss in the uplink is 148.5 dB, and the maximum path loss in the uplink, this is in the downlink, this is in the uplink, is also 148.5 dB. And in this case, it's a balanced link. Okay, so the link budget is okay. Maybe you have a question that is, assume that it's not balanced. Assume that the maximum path loss here, let's say the maximum path loss here, the maximum path loss here is, for example, 140 dB. What's happened? If you are working like this means that in downlink, if the user is here, okay, the path loss here, it will be 148.5 dB. This means the distance here, or if it's an obstacle, okay, but I'm talking about the coverage. This means that the terminal of the user is able to detect if we work at this path loss, okay? So in the uplink, it will not be the same. So if it's just 140, this means that the user should be more closer to the base station, or in this case, if the user is sending the signal from here, the base station will not receive the signal, okay, because the maximum path loss is 140, okay, or the user should be closer to the base station in order to let the base station receive the signal of the mobile. Okay, so if you want, it's clear now. If you have any question, you can ask me or you can send me a message. Okay, so this is for the uplink, and this is for the link budget. So we will see in an exercise that we should take into consideration the coverage in a way that the mobile station should receive from the base station and send to the base station. Okay, this is an important part to achieve the coverage. Okay, so let's now move to another important part in cellular system, which is the mobility management, and we have different situation here because it's cellular system. So it's the user is typically in mobility, is moving, okay, and we have different situation. The mobile station, it could be turned off. If the mobile station is turned off, this means that the mobile cannot be reached by the network because it's not answer a paging message. This is what when you turn off your mobile, and in this case, your mobile will not inform the system about your location because it's not working. And in this case, the mobile station is considered as detached. So if anyone call you, in this case, they will receive a message that you are not connected. Okay. And there is other situation where the mobile station is turned on, but it's in an idle state. It's an idle state. And in this case, the system can page the mobile successfully. So when this is the state typically when the mobile is switched on, and in this case, when it's switched on, the system will run the paging using paging channel, and based in this page channel, it's a kind of synchronization to let the system be aware that the mobile is now in the system. And if in case there is some message destinated to this mobile, or any SMS, or there is a call, for example, or a voice message call for this users, in this case, after paging, locating it, the call or the message is forwarded to this user. Okay. Uh, there is the third situation where the mobile station is in conversational mode. So in this case, it is that you receive a call, you are within a call. Uh, maybe you call it another person or you receive the call. So in this case, you are in conversational mode. And in this case, the mobile station is considered as busy and the radio network has traffic channel allocated for the data to and from the mobile station from this mobile. And when moving from one cell to another cell, the mobile station must also be able to change to a new traffic channel as the signal on the traffic channel drop below an acceptable level when the mobile is moving from one cell to another cell. Okay, in this case, the mobile is on a communication, and when moving here, the signal received from cell 1 is the strength of the signal is decreasing. However, the signal received from the cell 2 is increasing. So at certain level, there is a decision to trigger the handover between the cell 1 to the cell 2. So this message is we call handover, and it's possible also to call it handoff. So let's see together what are the different type of handover. And remember that the handover is just in the case where the mobile is in the conversational mode. Okay. So this is typically the synchronization, how it is done. Let's say you turn off your power, you turn on your mobile. So the first thing is to scan for the channel, okay, and to make synchronization in order to select the channel with the highest radio frequency. After that, you scan the channel for the correction of the frequency, which is frequency correction burst, in order to synchronize your receiver on the right frequency. When detected, you can pass to the next step. If not, you can select with the other radio frequency level from the control list. Okay. If it's okay, you are synchronized on frequency, so you are not camping on the right frequency. The mobile should synchronize in time, should achieve the synchronization in time, and in this case, it's in synchronization channel (SCH) channel in order to know the synchronization in the time. If it's detected, it's okay. You can go to the next step. Otherwise, you have to change also another frequencies in order to be able to camp to the right channel. Then if it's okay, you are now synchronized. So it's possible now you know which frequency and you know the start of each frame. Okay, so you are synchronized in frequency and time. Here the mobile will read the data from the broadcasted command channel, okay, that contain all information regarding to the cell. And if it's okay, so you are considered as camping to this cell. Okay, and now you are able to receive or to call or to make a call and so on. If not, if there is no broadcast channel, in this case, there is another way to select for another another radio frequency channel. This case maybe could happen, for example, if you want to try to connect to another operator, for example, but you don't have the right to connect to this operator. In this case, you select the signal of your operator, for example. Okay. So another important mechanism in cellular system, which are cell reselection and location update area. And remember those location updated area when we presented the temporary identity, the TSMI, okay, which is a temporary subscriber mobile identity. And as the network need to be able to forward any incoming call, so the subscriber location must be known. And remember that the subscriber location must be known while preserving the privacy of the users. So after the mobile device is switched on, its first action is to register with the network, and the network becomes aware of the current location. So as we said, the network will be aware about the location of the users, and typically this location is registered as the visitor location register. And we know that in the core network, we have HLR, where we have the right identity of the user. Okay. So here in this case, because in VLR you are using the temporary identity, so the network is aware about your location, but it's based on your temporary identity. So when moving from one location area to another location area, so the network informs the mobile device via the broadcast command channel, the cell idea, and the location area code. Okay, so in this case, the mobile device has to report only its new location if the new cell belongs to the new location. So in this case, so the mobile is in location area 5. When moving on location area 5, the mobile will not report its location because the first time it's done. When moving to location area 4, for example, and at this level, when receiving information that you are in location area 4 and the previous information locally was that the mobile is in location area 5. So in this case, the mobile device will report its new location to say that I'm in location area 4, okay? And this is registered at the VLR. So that's why when moving from cell 1 to cell 2 or from cell 2 or cell 3, if even moving between two cells within the same location area, the mobile device will not report the new location, okay? And after that, when the mobile station is in the conversational mode, in this case, the mobile station is busy and the radio network has traffic channel allocated, as we said. And the idea here is to to know in this case how this process of handover is done. And in this case, the handover procedure is divided to three main phases. The first phase is the monitoring and link measurement, which is the continuous process in order to maintain the quality of the communication. So the link, the communication quality will be monitored in order and measured in order to maintain its quality. And after that, there is the process to determine the target cell and to trigger handover, and we will see how it's done. And after that, we execute the handover. So when we trigger the handover, then we go to the step of the execution, which is the allocation of the resources in the new cell and the camping to the new cell. So the handover is typically initiated because a variety of reasons. Why we trigger a handover? So typically, the typical case was that if we are in a cell and we are moving, so typically we have a degradation of the quality of the signal from cell 1. So that's why we have to move to a cell with the best signal, with a better signal. So one reason is the signal strength deterioration, which is the most cause of handover at the edge of a cell. This is typically the case, but now with the new generation of cellular system, it's possible also to have, for example, to trigger handover for load balancing, or it could be an handover initiated by the network to avoid traffic congestion or something like this. For example, assume that the user is here at the edge. Okay, the user is here at the edge, and we have different cells. Even if the quality is good in cell 1, it's not at the bad level, and we are able to collect data from to receive signal from cell 2, and it's possible to make handover. For example, the decision in this case could be initiated by the network to make load balancing because cell 1 is loaded. You have a lot of load in cell 1, but in cell 2 you don't have a lot of users. So maybe in this case, the operator or the system will react in a way that the the mobile will make the handover to cell 2 to make some, let's say, load balancing between cell 1 and cell 2. And in this case, it's not initiated by the deterioration of the signal. Okay, this is another case that's possible to trigger the handover. So typically, in the rest of this part, we will focus on the handover initiated by the signal deterioration, and let us to see what are the different handover triggering algorithm that are known in cellular system. Here we have different, let's say, uh, uh, parameter or that are measured at the mobile station and at the base station, and we have the received level of the signal at the base station is the received power level of the neighboring base station and BS on the downlink or on the uplink. So in this case, the mobile will receive the level we is able the mobile station, which is the terminal equipment of the user, is able to know the level of the received signal from base station and the received signal in uplink and downlink of the current base station, which is the base station that is where the mobile is currently camping. And typically one of the simple algorithm, which is the received power of any base station from the neighboring. Those are typically the neighboring base station. Okay, typically they are the neighboring base station, and in this case, if the signal is greater than the current, it triggered an handover, but it's not a good algorithm because let's say you are at the border and when you move slightly in this direction, you trigger an handover, and after that, due to another conditions, you just return for let's say for a short distance, and in this case, the signal here will be better, and you will have a ping pong effect. So that's why it's better to have, let's say, a more advanced algorithm. Another problem is that if it's very bad the quality here, and also it's not a good quality here, but it's better than this one. In this case, it will trigger an handover. So that's why we have to add two things. The first one is to have a threshold. So in this case, if the received signal from the target base station is better than the current base station, and it's also the received signal from the target base station, it's better than a certain threshold. So in this case, you are sure that it achieved the required quality, and it's also possible to implement it to be less when the when your uh, when the base station the received power from the current base station is less than threshold. It's another implementation, but it's the same idea. And it's also, as I said, it's also possible to add what we call certain hysteresis, which is a certain delta, which is a certain difference when the received signal from the neighboring base station is better than the current base station, but plus a certain time. So when you leave your current base station to the best one, in this case, the signal here is decreasing at certain level, but you will switch to the another one, not just when the received power from this base station is greater, but it's greater with a certain hysteresis, so to be up, so to avoid the ping pong effect. In this case, if it is greater than the current the received power from the current base station plus a certain hysteresis, it's okay, you can switch. Okay, and in order to be sure that this power here is with good quality, this is the best one where you can use relative signal power with hysteresis and threshold. So you should be sure that the received power from the neighboring cell is better than your cell plus a certain hysteresis. So it's here, and also here it's greater than a certain threshold to achieve the quality of service. And this is typically what's implemented in cellular system. This is the general idea. Okay, this is the general idea. We can implement it also to be greater than the current base station power plus a certain hysteresis, and when this one the power of the current base station is less than this certain threshold, is the same idea but implemented in a different way. Okay. So I hope that it was clear for you. So after triggering the handover, okay, so we at each time the mobile and the system will monitor the link from the current base station and from the neighboring base station. This is what we call monitoring and measurement. So at each time they will measure them. When this algorithm is validated, so when this algorithm is okay, this means that when you have the received power from this base station, cell 2, is greater than the current base station plus delta here, and it's greater than the threshold. In this case, we trigger the handover. So the objective here is to trigger the handover. And after that, you have the process of handover execution. And during this process, the channel will be reserved for the users here. And at certain, we could have a small part of time where the user is connected to both cells, which that's what we call it handover. And after that, the user will switch to the next cell. Typically, we call it make before break. It's also possible that break before make. In this case, uh, we we leave the channel here and we reserve the channel here. It's possible in this case to have a small interruption. If it's done very fast, it will not be seen by the users. Okay, so those are typically the handover, uh, let's say, types. And let's see other handover scenarios. As we said, we have it's possible that we have two cells that belong to the same base station controller. So in this case, we call it intra base station controller. So the allocation of the resources will be done, which is intra, so the same base station controller. If the user is moving from one cell under the control of one BS to another cell which is under the control of another base station controller. So in this case, we call it enter base station controller, and the information to allocate everything will be done at the mobile switch center in order to make the allocation. Okay, and there is another third case where here they are under the same. It's possible that we have two mobile switch center from cell 4, for example, to cell 5. Cell 4 is under this base station controller. Cell 5 is under this base station controller. And those base station controller are under the control of different mobile switch center. So in this case, we have two mobile switch center that are involved to execute this handover. Okay. So that's why it's very important to understand the handover scenarios and the execution. So for the execution, the main idea, as I said, is to be able to make the reservation of the communication. So let's say it's let's say the user moving from this cell to this cell is receiving a call. If it's between cell 1 and cell 2, it's just intra base station controller. So there is no change at the mobile switch center. And at the base station controller, the idea is to reserve resources here and after that to free the resources here. Okay. When moving from this side, from cell 2 to cell 3, in this case, the mobile switch center will be involved in order to reserve the resources at the base station controller and at these cells. And if the handover is between cell 5 to cell 6, so you have the mobile switch center B and the mobile switch center A, they are involved in order to reserve the resources at the mobile switch controller and at the base station 3, okay, and at the cell 5, okay, sorry, from cell 4 to cell 5 and at the cell 5. And in this case, after that, to free the resources here. Okay. So I hope that it was very clear for you. This is the different signaling that are executed. For the example of the intra base station controller, the idea is that the mobile station is communicated with the old base station. Okay, and now try to connect to the new BTS after the handover triggering. So the base station controller will be in charge. It will be uh, it will reserve or allocate a new TCH channel for this user at the new BTS, and make the act and give the handover command to the mobile device. And after that, the mobile device will change to the new BTS, okay, and will establish the communication. And after that, we redirect the connection, okay, and now we consider that the performance it's okay, and the mobile device will use the resources at the new BTS, okay. And as we said, we inform the all other devices from the mobile switch center side. Okay. So this is typically, we can also give the details regarding enter base station controller and enter mobile switch center, but it's a kind of signaling. The idea is to understand the concept of and the difference between the different scenarios. Okay. Let's see that at this level we have now a good, let's say, uh, view and a good overview about cellular system, mainly the second generation GSM. We still have some exercises, mainly on link budget. We will see them together. Okay, and after that, we can move to chapter 4 to see UMTS. So I will complete the exercises regarding chapter 3 for GSM, and after that, we move to chapter 4. Okay. If you have any question, please, you can ask. Okay.